Welcome to Python Probability and Statistics. In this hands-on notebook, we will explore core ideas of probability and statistics using Python. You do not need any previous math or coding experience. Let us get started step by step with small, fun examples. Running the cell now. First, let us set up our notebook to work with probability and statistics. This step prepares your notebook by importing essential Python modules commonly used for data, statistics, and plotting. This line tells Python to ignore warnings, so our notebook stays clean. NumPy is for fast number work, especially arrays and probability. Pandas is used for organizing data in tables. Seaborn helps with nice, quick charts, and also includes sample datasets. Matplotlib is the workhorse for plotting and visualizations. Running the cell now. Try running this cell to see that your notebook loads all libraries without errors. 1. Probability, the basics. Probability is a way to talk about how likely something can happen. Let us start with coin flips and dice rolls. Running the cell now. Let us see how Python can model the chance of flipping a coin. We are coding a virtual coin flip. Heads is H, tails is T. This line randomly chooses H or T, just like flipping a coin. The print statement shows you the outcome right after the flip. Running the cell now. Run this cell a few times and notice how the result changes. Which side comes up more often when you repeat? Rolling dice is another classic example in probability. This simulates rolling a regular die with sides labeled 1 to 6. The random integer line randomly chooses a whole number from 1 up to 6. The print line shows which number turned up on our virtual die. Running the cell now. Try rerunning to see all possible results. How would you simulate a 10-sided die? 2. Descriptive statistics, summarizing data. Descriptive statistics help us understand and talk about patterns in data. We can calculate averages, medians, and more. Running the cell now. Let us summarize a set of test scores using 3 key numbers. We have some scores that could come from a real classroom. NumPy's mean function finds the average, adding all and dividing by count. Median gives us the middle score when sorted. The mode is the score that appears most. Series.mode in Pandas makes finding the mode easy, and values, 0, just gets the first one. Now, the full list is shown so we can see what we are summarizing. The mean is printed so we see the average clearly. The next print shows the median, revealing the middle. Finally, the most common score, the mode, is displayed. Running the cell now. What do you notice about the scores? Which summary, mean, median, or mode, seems most helpful? Sometimes real data has gaps or missing spots. Let us see how to work with missing values safely. We create a new scores list and use np.nan to mark missing entries. Pandas makes handling missing data easy. Dropna removes those missing spots for us. We can then find the average on only the non-missing values. Here is the list with missing values shown using nan for not a number. We print the clean mean that ignores missing values, so our summary remains true. Running the cell now. Check how mean changes with and without missing data. What might cause missing data in real life, like surveys or sensors? 3. Discrete distributions. Probability with counts. Discrete distributions describe outcomes we can count. Let us look at coin flips, dice, and real-life counts. Running the cell now. Let us repeat a coin flip 10 times to model a Bernoulli process. Bernoulli just means 2 outcomes, like heads or tails. Here we repeatedly flip a coin, 0 is tails, 1 is heads. Randomly choosing between 0 and 1 models each flip, 10 times. The results show every individual flip in one list. Summing those results counts how many heads we got out of 10 tries. Running the cell now. Rerun this cell. How often do you get 5 heads? What about all heads or all tails? This is the building block for modeling many yes-no processes. The binomial distribution summarizes outcomes of several Bernoulli experiments. For example, 20 flips of a coin. We import binomial from scipy.stats to simulate grouped coin flips. We simulate flipping a coin 20 times. Binom.rvs returns one number, telling us the number of heads out of 20. Now we see how many heads came up in this simulated trial. Running the cell now. Try running this cell more than once. The number of heads should be close to 10, but can vary. Can you change P to see what happens with a biased coin? The Poisson distribution models the number of times something rare happens in a fixed period. For example, phone calls to a support line. We import Poisson from scipy.stats to model how rare events pop up. Mu is the expected average number of events per time unit. Here it is 2 calls per minute. We simulate the number of calls received in 10 random minutes. This prints out how many calls happened in each of those 10 minutes. Running the cell now. Rerun this example. Notice the count sometimes jump up or down. What rare events could Poisson help you model? For continuous distributions, the world of measurements. Continuous distributions help us model measurements, like height or test scores. Let us see the normal, bell curve, and exponential distributions in action. Running the cell now. Let us create and visualize a set of random heights from a normally distributed population. Normal means a bell-shaped distribution, with most people near the average. NumPy's normal function simulates 1,000 adults' heights, centered at 170 centimeters and mostly falling within 10 centimeters above or below. This line actually creates that random height data. We make the figure a bit wider for clear plots. The next line draws a histogram using Seaborn, showing the height spread plus a smooth curve. A title is added for clarity. We label the x-axis with centimeters. plt.show displays our chart beneath the code. Running the cell now. Look at the shape. Can you see the bell curve? Think about what kinds of real-world data tend to look normal. Now let us see waiting times, what we experience between random arrivals. The exponential distribution is common for modeling waiting until the next event. This line uses NumPy to simulate 500 bus wait times, averaging 5 minutes each. We plot these as a histogram, which can show there are many short waits and few long ones. Adding a title helps us keep track of what we are looking at. Labeling the x-axis lets us know we are measuring minutes. The y-axis shows how many trips fell into each wait time group. Finally, we display the result below. Running the cell now. Notice the shape. Do most people end up with a short or long wait for their bus? Try changing the scale to see what a faster bus does to this pattern. 5. Sampling and the central limit theorem. Sampling is when we take a smaller group from a big population. The central limit theorem says averages of samples become normal-shaped, even if the original data are not. Running the cell now. Let us prove the central limit theorem with a small demonstration. We start with a very non-normal dataset, then take many random samples. We simulate a large population of 10,000 numbers with an exponential distribution. For each sample of 50, we take a random group and calculate their mean. This repeats 200 times. These are all the sample means put together. A histogram displays the distribution of those means. Here we add a clear and descriptive plot title. Label the x-axis so we know what these numbers mean. Show the plot for quick comparison. Running the cell now. Notice how the means start to form a bell curve, even if the data itself was not normal. Try changing the sample size to see what happens to the shape. 6. Confidence intervals. Confidence intervals tell us how certain we are that a true value falls within a specific range. They are used everywhere, from surveys to science. Running the cell now. Let us find out how sure we are about the average tip from a sample of restaurant bills. We sample 50 total bill values from the popular tips dataset for variety. Mean finds the sample average tip value. STD gives us an idea of how much the tips vary up or down. We import the t-distribution, which is good for small groups. This calculates the lower and upper bounds for our 95% confident range. Printing the mean, we quickly see the center of our data. Next, see the confidence interval, meaning the true average will probably be within this range. Running the cell now. Think about what it means if the interval is wide or narrow. Where might you see confidence intervals used on TV? Let us test if there is a real difference in tip sizes for smokers and non-smokers. We will use a statistical test called the t-test. We load the full tips dataset for variety. Filter out just the tips from smokers, so we have a group. Now get the non-smoker group too. Import the test_int function to compare the groups. This runs the t-test, asking, is the difference real or random? We print out the tip average for smokers, so we see what is typical there. Same for non-smokers for easy comparing. The p-value tells you if the difference is likely due to chance. Below 0.05 often means it is real. Running the cell now. Try comparing other groups in the tips dataset, like day of the week. Do you think the difference is surprising? 7. Correlation and covariance. Are two things related? Correlation shows if two variables tend to move together. Covariance is a similar measure, but not scaled between -1 and 1. Running the cell now. Let us check if cars with higher horsepower get lower gas mileage. We will use pandas to calculate both correlation and covariance. Loading the miles per gallon dataset, we make sure to drop missing values so math works right. Call returns the Pearson correlation coefficient. 1 means very related, -1 is perfectly opposite, 0 is not related. Cov shows the direction and size, but not scaled. It is useful, but most people prefer correlation. These printouts let us make sense of how horsepower and fuel efficiency are linked. Running the cell now. Do your results match your guess? Try plotting the relationship in the next cell. Pause and think about other pairs you could compare. Let us visualize the two variables together. Scatterplots show each car as a dot, connecting two features visually. We label the axes to keep track of what each value means. Label the y-axis for clarity. Add a clear title above the plot. Finally, show the figure for review. Running the cell now. What pattern do you spot? If you see a downward trend, you discovered negative correlation. 8. Simple regression, making predictions. Regression helps us guess one value based on another. Let us build a basic prediction model for miles per gallon from horsepower. Running the cell now. Now let us train a model to predict miles per gallon from horsepower. We will use a very common method called linear regression. First we bring in linear regression from Sklearn, a standard tool for machine learning. X holds our predictor. Here, just horsepower, kept as a data frame for Sklearn. Y is the outcome we want to predict, miles per gallon. We train, or fit, the model using horsepower to predict miles per gallon. Slope is printed. It tells us how much miles per gallon changes for each extra horsepower. The intercept is where the prediction line crosses if horsepower was 0. We use the model to guess the miles per gallon for a car with 100 HP. Printing the prediction gives practical meaning to the regression. Running the cell now. Try predicting the miles per gallon for cars with higher or lower horsepower. Notice, models are only as good as the data they see. 9. Logistic regression. Will a passenger survive? Logistic regression handles problems where the answer is yes or no. Let us use the Titanic dataset to predict survival. Running the cell now. Let us load the Titanic dataset and check the shape and a preview. This cell loads the built-in Titanic dataset, making sure to drop missing values for needed columns. We check the number of rows and columns for a quick size check. Head, let us look at the top part of the dataset. Running the cell now. Notice how the columns include age, fare, sex, and survival. Think about what questions you could ask with this information. Now we will predict if someone survived or not with logistic regression. Import logistic regression and a helper for splitting data into training and testing parts. Get_dummies changes text categories, like sex, into ones and zeros for modeling. X holds features like age, fare, and class. Drop first avoids dummy trap. Y is whether someone survived. Here we split the dataset, 70% for training, 30% for testing. Set up the logistic regression model, allowing up to 1,000 loops to be sure it finishes. We fit, or train, the model with our training data. Score tells us how often our model got the test answers right. Print the accuracy to see how well our model performed. Running the cell now. Try changing features or changing the split size. What improvements to survival might you spot across different groups? 10. Time series, airline passengers. Time series data tracks values over time, like months or days. Let us load and plot the number of airline passengers each month. Running the cell now. Next, let us get data for monthly airline passengers from a real CSV file. We read in the airline passengers CSV directly from a public GitHub link. Printing the shape checks how many rows and columns we have. Show the first few entries, usually with head. Running the cell now. Notice that our time column is labeled as month and we have a column named passengers. Think about what trends or seasonality might show up in this data. Let us visualize how air travel changed over the years in this dataset. We plot the monthly passenger totals against date. Add a label to the month axis for clarity. Label the y-axis with what we are counting. Give it a helpful chart title. Rotate the X-tick labels to keep month names readable. Tight underscore layout ensures nothing overlaps. Show the line chart for easy pattern finding. Running the cell now. What patterns do you see? Is air travel constantly rising? Check for dips or peaks that repeat in the same month every year. 11. Bayesian statistics, updating beliefs. Bayesian statistics allow us to update our beliefs as we see new data. Let us try a toy example using a beta distribution. Running the cell now. Let us show how seeing coin flips can change our belief in whether a coin is fair. Bayes' theorem lets us update with new evidence. Import the beta distribution, which models beliefs about probabilities. A and B set our initial belief, beta, 1, 1, is completely unsure, a flat line. Update to beta, 3, 2, after 2 heads and 1 tail, this means we think heads is now a bit more likely. X holds all possible probabilities between 0 and 1. Plot the old belief, the prior, as a curve. Plot the new, updated belief, the posterior, to see the update. Label the x-axis, which runs from 0% to 100% heads. Label the y-axis to show our confidence. Add a legend so both lines are clear. Give the chart a simple but clear title. Show the graph to reveal how learning changes our beliefs. Running the cell now. What would happen if you saw 10 heads and 1 tail? Try changing the parameters. This is a powerful way to reason with new evidence in science and everyday life. 12. Mini project, simulate and analyze. You have learned many tools. Let us apply them in a fun 2-part project. First, let us simulate dice rolls and look for patterns. Running the cell now. We will roll 2 dice 500 times, add up the results, and plot the sums. Simulate 500 rolls for the first die. Repeat for the second die. Add the pairs together to get the total for each roll, just like in games. Plot a histogram of the sums. Range 2 to 12 covers all possible totals for 2 dice. X-axis labels show which sums are possible. The y-axis tells us how often each sum appeared. Our title explains exactly what the plot is about. Show the completed plot. Running the cell now. Which sum is most common? Why do some totals happen far more often? Try increasing the number of rolls to 1000 for a smoother shape. Now let us use real data to compare survival rates for different groups on the Titanic. Group passengers by both gender and ticket class. Calculate the mean to get survival probability. Print out the chart for a quick table view. Next, plot those group averages as bars to see patterns more clearly. The chart title explains what each bar means. Label the y-axis with what is being measured, survival rate. Label the x-axis for clarity, showing groupings by sex. Make group names easy to read by not rotating them. Show the finished grouped bar chart. Running the cell now. Practice, choose another column from the dataset and make your own grouped chart. If you enjoy the project, please give the video a like and subscribe for more Python lessons. 13. Best practices and troubleshooting. Always check your data for missing or strange values. Use plots to spot patterns quickly. Rerun cells if something looks odd, sometimes random examples will change. Running the cell now. 14. Extra tips. If you get errors, double-check spelling and capitals. More datasets can be found at Seaborn Data or UCI Machine Learning Repository. Try adding your own comments above code blocks to help you remember what each does. Running the cell now. Let us finish with a coding challenge. You will pick how many coins to flip. Here we allow you to enter any number for fun custom coin flips. Try lets the code work even if you make a mistake entering your number. Input prompts you and makes sure it becomes an integer. We flip your chosen number of coins. Print out every coin's result for review. Also print the total head so you can estimate the probability. Accept catches any errors and suggests what to do next. Print a helpful message if there is a problem. Running the cell now. Try changing the number to something unusual, like 3 or 100. Let us know in the comments what number you picked and what surprised you. 15. Recap. In this notebook we learned basics of probability, worked with real and simulated data, explored statistics, regression, and more. Keep practicing and check out the extra resources below. Running the cell now. Join us. Like and subscribe. If you enjoyed learning, consider liking the video or subscribing for more hands-on Python and data science practice. Share your favorite lesson in the comments. Running the cell now.